two loose ends have been trailing through this entire course. First, what exactly is a density once there's no dx left to divide by? And second, what does the word given actually mean? One theorem answers both, the Radon-Nikodym theorem, and the answer to the second turns out to be pure geometry. Start with two measures living on the same space, our probability measure P, and a second one, Q. Say Q is absolutely continuous with respect to P if every P-null set is also Q-null. Whenever P of A is 0, Q of A must be 0 too. Q cannot put mass anywhere, P sees none. The Radon-Nikodym theorem says that condition is exactly enough. If Q is absolutely continuous with respect to P, there is an essentially unique non-negative function f, such that Q of A equals the integral of f over A with respect to P for every event A. That f is the Radon-Nikodym derivative, written dq by dp. It is a density in the fullest sense of the word. Not a density with respect to length, but with respect to whatever base measure you choose. You have already met it 3 times. An ordinary probability density function is dp by d Lebesgue measure. The likelihood ratio from the Neyman-Pearson lemma is dq by dp for 2 competing distributions. And in Bayesian updating, the ratio of posterior to prior is a Radon-Nikodym derivative as well. Now the second loose end. Let G be a sub-sigma algebra of F, a coarser collection of events, standing for partial information. Not everything F can resolve, only what G is able to see. Conditional expectation, E of x given G, is not defined by a formula. It is defined by a property. It is G measurable, and for every A in G, the integral of E of x given G over A equals the integral of x over A. The same total mass on every set G can distinguish. Why should such an object exist? Define nu of A as the integral of x over A for sets A in G. That is a measure on G absolutely continuous with respect to P. Radon-Nikodym hands you its density, and that density is E of x given G. The 2 halves of this lesson are one theorem. Now the geometry. Take L2, all random variables with a finite second moment, equipped with the inner product of x and y defined as E of x times y. That inner product turns the space into a genuine geometry, where lengths, angles, and orthogonality all mean something. The G-measurable variables sit inside it as a closed subspace. And conditional expectation is precisely the orthogonal projection onto that subspace. E of x given G is the point of the subspace closest to x. The residual x minus E of x given G is orthogonal to every G-measurable variable, that is the defining property, rewritten in geometric language. It is also why E of x given G minimizes the mean squared error over everything G can see. Conditional expectation is the best prediction the information allows. And the Tower property falls straight out. If H sits inside G, then projecting onto G and afterwards onto H is the same as projecting onto H directly. E of x given G given H equals E of x given H. Nested subspaces, nested projections. The Radon-Nikodym derivative, dq by dp, is what density means when there is no dx in sight. And conditional expectation is exactly that derivative, for the measure sending A to the integral of x over A, restricted to the information in G. Geometrically, it is a projection, the closest G-measurable variable to x, the best guess the available information supports, with an error orthogonal to everything you already know. That completes the measure-theoretic track, and the roadmap along with it. From sample spaces and counting arguments back in Lesson 1, to conditional expectation as an orthogonal projection here in 57, the same subject all the way down.